Okay. Yeah. So people are already logging in. While our attendees are connecting, I'd like to give you a very warm welcome to this installment of the European Microwave Association's webinar series. Today I have Bartosz with me, whom I will introduce in a few seconds in more detail to you. Before that, I'd like to give just some um, advertisement as always, as those of you who have attended the series before might know. So I've just for a very few moments, I'll give you an overview over the European Microwave Association and the webinar series. So as said, today is Bartosz with us, who's with Hamburg University, and his talk will be on short range phenomena in radar-based sensing. Um, yeah, and if you have interest in our recorded webinars that we have done before, please feel free to just Google it or whatever you like. So you find them on YouTube on the channel, the European Microwave Association. So I'm sure you will find out. And there are lots of topics that are also very interesting, and we had a very interesting discussion also in those webinars. What I'd also like to just point out is that, of course, we will have a European Microwave Week this year again. So it will be in London in the Excel Conference Center in the beginning of October. And it will feature, as always, the three major microwave-related conferences: the EuMIX, the European Microwave Integrated Circuits Conference, for those of you who are interested in integrated microwave topics, the very broad European Microwave Conference, and the radar-specific European Radar Conference at the end of this week. In addition to this, we will, of course, have a very nice exhibition with major companies from the field. We will have student schools and doctoral student schools in the field of microelectronics. And I've seen there's a student design competition related to OFDM signals as well. There are young professional events and a career platform. So even though the deadline for paper submission has already passed, you might want to register for the conference and just have a visit there. What has not yet passed is the deadline for those of you who are students. So if you are a student and you'd like to help us running this conference, you can sign up as a volunteer or apply for a volunteer position, which basically means you will get a hotel stay for the whole week in exchange for 2 to 3 days of work at the conference. That means you'll have to check the badges, for example, in the session rooms, or help with the coffee breaks or whatever organizational topics. And in exchange, you get free access to everything, and even the hotel stay in London, which is, of course, also very interesting. So here's the deadline, will be on June the 1st. Okay, and with this, I'd like to come back to our topic today, back to Bartosz. So we'll just briefly introduce him to you. So Bartosz received the Bachelor of Science and Master of Science degrees in engineering from Hamburg University of Technology. He's currently pursuing his Ph.D. there, and his works are already have been awarded with a lot of prizes. He won the design competition at the IMS, the International Microwave Symposium, in 23, the Best Student Paper Award at the German Microwave Conference GEMIC in 2024, the Young Scientist Award of the International Radar Symposium in 25, and last year the Young Engineer Prize of the European Microwave Conference. And his research currently includes passive components, measurement techniques, electromagnetic theory, and modeling and simulation of radar systems. So a very bright range, and I'm very happy to have you here, Bartosz, today. And with this, I'd like to hand over to you.
Yeah, thank you very much, Jan, for the introduction and also for the invitation and the possibility to present a part of the research topics you mentioned. So it's not all about all of the spectrum, but only the part of radar and modeling of scattering. So welcome everyone to this presentation. First of all, I would figure out to share the slides with you. So I hope they are visible now.
Yeah, looks good.
Okay. Yeah, so the topic of today's webinar is the short-range phenomena in radar-based sensing. Radar technology is a very widespread technology used for different kinds of application. There are the classical ones, which are devoted to localize or detect targets at far range, but there are emerging applications that shift the radar and the target closer to each other. And here I've provided a classification, a broad overview of those short-range radar applications. So on the left-hand side, we see the class of industrial applications. There are a lot of different application types. Just to name a few is our positioning of machine or monitoring of vibrations of rotary machines, also the non-invasive testing of materials and their properties, and also the monitoring of safety areas around machines, for instance. On the right-hand side, we see the automotive domain. And in the automotive domain, there are a very well-established part of radar technology devoted to the exterior of the car, right? The collision avoidance radar, for instance. But also the current trends are also to use radar technology to monitor the inside of the car, for instance, related to presence detection, awareness monitoring, but also vital sign sensing of the driver. In the center, I see also the very interesting topic of medical radar, where the radar is used to sense vital activity of patients. And this allows long-term monitoring in hospitals, for instance, where not only the, let's say, long-term heart rate is of interest, but individual heartbeats and medically relevant parameters such as the heart rate variability. And since the radar and medical radar applications sense the body or the mechanical movement of the body surface, there's also interest in terms of medical research to apply radar to get new insights in the activity of human bodies. In the next slide, I would like to focus a little bit as an example for the medical radar applications, just to get an overview about the important relationships regarding short-range radar applications. And here you see an overview slide, what's important when dealing with medical radar applications, just as an example. So on the left-hand side, we have a radar sensor, and on the right-hand side, with the human body, which from the perspective of radar serves as a target. And this body is subject to different mechanical movements, and these are related to the vital activity. So usually one classifies the respiration, which leads to a displacement of the human chest with a certain frequency range of operating here. And we have also heart activity, which is linked to two different physical phenomena, such as the pulse wave and also the heart sounds. And those effects induce changes of shape and vibrations on the skin surface, which range from centimeters to micrometers, right? So the centimeter range is devoted to the respiration, where the chest wall moves up and down while breathing, and the micrometer regime is devoted to the heart sounds, which are related to the acoustical wave which is produced by the heart. And the task of the radar sensor is to measure those vibrations, and from this deduce vital sign parameters. So we have a very broad range of very small movements ranging from centimeter to micrometer, and these radar sensors in those short-range configurations need also high resolution as well as accuracy. In order to understand radar technology, or how the radar signal is received by our radar transceiver, I've brought to you this slide, which will just summarize all of the classical relationships which are used to understand radar. And here, for simplification, we assume continuous wave operation. Right? So, for instance, the medical radar application, since only measures vibrations or relative displacements, is also sufficient to challenge this task, but also the continuous wave operation mode allows to generalize the short-range phenomena, which I will discuss in this presentation, to other radar technologies such as FMCW radar. So looking at this slide, we have an antenna on the right-hand side, which is fed by a radar transceiver, which generates a certain input wave. And on the left-hand side, we have a target. So the antenna produces this wave of a certain wavelength, and because of its radar cross-section, the target reflects the wave such that at the radar transceiver, we have a received sinusoidal wave, because we are dealing with continuous wave operation, with a certain amplitude shift or an amplitude deviation and a phase shift. And in order to describe, for instance, what the receive power is, a very fundamental equation, of course, is the radar equation. So here we see the ratio of the receive power to the transmit power, which are linked by the gain of the antenna, the wavelength, the distance, as well as the radar cross-section sigma. So this is the one part devoted to the amplitude of the received signal, but also we have a time delay, right? So because of the time delay, we can measure distances as well as mechanical vibrations, for instance. And for continuous wave operation, the time delay translates to a phase shift. This phase shift is linked with the distance, and this way one can also deduce the relative movement of a target. Okay, having all of these quantities, actually one would say, okay, we can predict what the radar receive signal is, but there are certain assumptions usually made to these equations, and this is that the range is significantly larger than the target size, or that the range all in all is very, very large. But in short-range applications, the antenna and the target, they move closer to each other. And this triggers the question whether those basic relationships are still applicable in this short-range configuration. And this is basically the motivation for this talk, which should answer the questions: which effects become relevant in short-range radar sensing that are typically neglected in classical models. And the picture here in the center of the slide shows what we're actually looking at. So we completely neglect the radar transceiver. We assume it is perfect, right? When we assume it's perfect, the only thing we need to care about is basically what we denote here as a radar channel. So what's happening between the antenna and the target. So the interaction between the antenna and the target, this is what we are looking for in this presentation, and we assume that the range between those two is becoming smaller and smaller. For this presentation, I will focus on three different effects. So these are listed here. So this is the self-radar cross-section of our own radar systems, how it affects measurements in the short-range applications. Then I will proceed to the near-field effects. And finally, a topic which is linked to those near-field effects, which, by the way, in my personal opinion, are the most interesting ones, is the radar channel variability. And the agenda of the talk is always displayed on the right-hand side. So for the ease of navigation, you can see at which topic we are currently on. Well, after this introduction, we'll directly proceed to the first topic, which is the self-radar cross-section, abbreviated as self-RCS. To begin with, I would like to show you this very simple setup. And again, we assume transceiver is perfect. We are not dealing with the imperfections of the transceiver. We are focusing what's happening between the target and the antenna. And for this, we use this very simple setup, where on the right-hand side, we have a basic 4x4 patch antenna array, which is connected to a vector network analyzer, which is devoted to measure the reflection coefficient calibrated with respect to this reference plane. And on the left-hand side, we have a target, a basic disk, 80 millimeter in diameter, at a distance of 1 meter. And we are operating here at around 24 gigahertz with a wavelength of 12 millimeter. And the task of this simple measurement is to move the target from its reference position, as shown in this animation here. So moving the target towards the antenna, and the task is to retrieve its relative motion as precise as possible. This is a perfect setup: vector network analyzer, no idealities, absorbers, and so on. And when we look at the measurement, this is shown in this slide. So for each position, for each sample, we are recording the measured input reflection coefficient of the vector network analyzer. And this is how it looks like. We're recording a circle in the complex domain here. And as the target approaches the radar, the measured reflection coefficients, draw a circle which draws counterclockwise. And this is very good. So when you want to retrieve the displacement, the typical thing is to see, okay, this looks as a circle, but there was a certain offset related to the input reflection coefficient of the antenna. So the first thing to do is just to fit a circle inside such that we can determine the offset. And the offset is here drawn as the cross here. And once we compensate for the offset, we get a new reflection coefficient. And from this reflection coefficient, we can easily determine the relative displacement as shown below, because the relative phase shift relative to the initial position is simply linked by a linear dependency. And this allows us that the relative displacement we estimate from the measurement basically is directly proportional to the measured phase shift, normalized to 2 pi, and it's scaled by half the wavelength. Of course, we have a periodicity ambiguity because of the periodicity in space of the wave according to the wavelength. Fair enough. With this, we can go and show what's the transfer characteristic of our ideal radar sensor. So on the right hand, on the bottom axis, we see the ground truth displacement of the target, and on the vertical axis, the estimated one. And in theory, because of the linear relationship, we obtain a perfect linear response. And when we look on the measurement, well, it looks also very linear. And at this position, you might ask yourself, what is he talking about? But the key difference is, what's the difference between those two curves? And when we observe the difference between the measured characteristic, the x hat, and the ground truth, we observe a periodical error. And the period is associated with half the wavelength. And the question is, where does it come from? So we had a perfect setup, fully calibrated network analyzer. We can assume it's a perfect hardware. Where does this error come from? And the answer to this question is the self-radar cross-section. Radar sensors are not invisible for radar themselves. When we look at this graph here, which visually tries to convey the message here, when we have a radar system which illuminates a target, the reflected wave, it's propagating toward the radar sensor, but it feels quite intuitive to say the target has a radar cross-section, and this is the basic operating principle of radar, that objects are scattering waves, but the same happens when the wave approaches our radar. And this is not only the antenna which contributes to this reflection, it's also the housing of our radar sensor, for instance, additional PCBs, which we are using for baseband processing or the storage of data, and so on and so on. And because of the self-RCS of our radar system, we have multiple reflections between the target and our radar sensor itself. And this is a relevant aspect when we are moving the target and the radar sensor closer to each other. To show you the scale of these effects, we did different tests. And here the test on this picture here is what we looked first, and a very basic example, but we used the very same antenna in different housing configurations, with a small housing, a larger one, and to mimic some processing PCBs, for instance, which are in practical systems, we are placing some dummy PCBs inside, and additionally, we can also apply some covers just to mimic real-world radar sensors in a laboratory environment. And when we perform the same measurement for all of these configurations, we have the same antenna, the same network analyzer, only the surrounding of our antenna changes. This is the error curves that we are observing. So all of them are periodic, but what we should observe is the y-axis scale. So for the small housings, the errors range up to 60 micrometers, but for the large housing, it's even up to 600 micrometers. And even though we have a perfect transceiver, the only thing which introduces this error is the presence of, or the physical presence of the radar sensor itself. And this is not only the accuracy which is impaired by this, but the other aspect is the linearity or the non-linearity of our transfer characteristic. If you look at this topic from this point, that we want to sense vibrations or oscillations of a target, we assume that the target motion, for instance, has some sinus curve, right? And if you have a transfer characteristic which is linear, the estimated target motion would also be a sinusoidal curve. That's what we want to sense, but and finally, if we would convey this in the spectral domain, we would obtain one spectral peak, of course, because of one frequency of the mechanical displacement. However, the radar itself leads to these multiple reflections and introduces this sinusoidal error on the transfer function. And finally, this leads to a measurement error, which also is periodic. And finally, the transfer function is not linear, and this leads to nonlinear distortion, which we can observe in the spectrum. So even though the target moves according to a perfect sinusoidal curve, what we are measuring is a sinusoidal response, but with a lot of nonlinear distortions. And this is something which we can also look at in the following slides with three different examples. The first example is very basic. So we assume that the target motion follows this sinusoidal curve. So it has an amplitude x naught and a mechanical frequency fm naught. Based on the measurements of the transfer characteristic we did in the perfect setup, these are the spectra we obtain. And just for a navigation, so the vertical axis is displayed in dB normalized to millimeter. So 0 dB millimeter refers to 1 millimeter amplitude. And what we observe is, first of all, the dotted curves are the ideal response. Of course, one spectral peak because of the single tone movement of the target, but we also obtain some harmonics here. And if we increase the oscillation amplitude, so here was a tenth of a wavelength, if we increase the oscillation amplitude, there are more and more harmonics arising. Even though we had a perfect system, only the surrounding of the antenna changed. The interesting thing here is that usually, for instance, dealing with mixers or so on, you would assume that the harmonics fall off with order. But here it's not the case. The actual spectral shape is determined by Bessel functions, if you do the math here. And this leads to the fact that also higher harmonics may carry more energy content than smaller ones. So we don't expect harmonic, that the power of the harmonics reduces with order, but it can even increase for higher order harmonics. In the second example, we show what happens actually with the target having a dual tone vibration. So we have the single tone vibration from the previous example, but we add another small amplitude vibration, which has an amplitude 1,000th times smaller and a higher mechanical frequency around 10.2. And here are the responses for an oscillation amplitude of 1 wavelength. The ideal response, again, is shown in with the dotted black curves, and the actual response we get from the measured transfer characteristics are shown by the colored bars. And what we observe is that the harmonics of the large amplitude oscillation, they can basically mask small amplitude oscillations. And this is critical when we look regarding, for instance, the medical radar applications, where we have vibrations ranging from centimeters to micrometers at different frequencies. And in context of this would lead to the fact that the harmonics of the higher amplitude oscillations would completely cover the smaller ones, which would make them hardly detectable. In the second example, this is also very, very interesting because we become, since we are dealing with a nonlinear system, we also observe some intermodulation effects, mechanical intermodulation effects. So we assume the target is moving with a dual tone motion, where both of the oscillation amplitudes have equal mechanical amplitudes, but they vary in frequency. And the response we get is a lot of intermodulation products. And the fact that there are a lot of intermodulation products, so even 100 times the fundamental oscillation frequency, is devoted to the bezel shape of the spectra, which can generate higher order harmonics, which then in the intermodulation show up with a very large mixing order. So to sum up, the self-RCS can lead to inaccuracies in our measurement and also lead to nonlinear distortions. So when we completely neglect the self-RCS, this is what we get. So the examples what we show here, they lead to a decreased accuracy in measurement and also masking of lower amplitude oscillation and also intermodulation effects. But the good thing is we can do something against it. So the first idea would be, let's try to minimize the size of the radar sensors such that we become smaller, and this would lead to a smaller self-RCS. But eventually the sensor needs to be applied somewhere or mounted on some wall or other mechanical setup, and this would also falsify or change the self-RCS. But the good thing is there is a calibration technique which can compensate for those errors. And this is what we want to focus in the next slides. So here, the modeling of this radar channel in this configuration can be done by a signal flow graph. And what we have here on the left-hand side is an ideal radar transceiver. It is connected to an antenna and an housing, which is modeled basically as a two-port device. Then we have the free space propagation, and ultimately we have the target on the right-hand side. And what we measure actually in our system is the reflection coefficient at this position, which accounts for the non-ideal behavior of the antenna. And the non-ideal behavior we are talking about is basically the reflection coefficient looking from the receive side of the antenna, not the transmit side, but from the receive side. So what the antenna and housing is reflecting back to the propagation channel. What we actually want to measure is basically at this reference plane, so in the free space reference plane to the target, such that we don't have the disturbing effect of the antenna. So the multiple reflections are going this way, and these are related to the reflection coefficient looking from the receive side of our radar sensor. If you make some certain assumptions, so for instance, a constant and range-independent RCS of the target as well as the radar sensor and spherical wave propagation, you can do the modeling, the math, and you arrive at a certain transfer function models. By the way, if you're looking for more details regarding the mathematical derivations, here are the QR codes, which brings you to the respective papers, which detail all of the derivations. So if you're interested in, you're highly welcome to visit them to study the math behind this. But in short, we have a transfer function model which describes the reflection coefficient we are measuring at this position, and it depends on certain parameters denoted here as P. And the most important parameter here is the parameter S naught. This parameter here basically is the key to describe the nonlinear effects associated with the self-RCS. So this is why I call them here the nonlinearity parameter. And if this parameter is 0, then the transfer function here is reduced to a linear phase dependency, which we actually would want to have in theory. But if it's not 0, we have this disturbing term, which leads to these nonlinear errors. And the nonlinearity parameter, it is proportional to the square root of the target RCS, the self-RCS of our radar system, and it also depends on distance, right? If the distance is increased very, very much, this effect becomes smaller and smaller. But since we are moving closer in short-range applications, this issue is becoming more and more relevant. Now, based on the transfer function model, we can do something similar as in vector network analysis or calibration of vector analyzer, a one-port calibration. It's a little bit different. It's similar. It's not exactly the same, but at the end, the all-in-all schematic or algorithm to do this is very, very similar. So first of all, we take some relative positions of our target, or we shift the relative distance between the target and the antenna and establish some system of equations based on our model and the measured reflection coefficients. Then we can solve for this nonlinear system of equations according to some criteria. So it's basically like curve fitting, and from this we can get our parameters, which just fully describe the model. From this, we establish the self-RCS calibration constant, which is key to then perform calibrated measurements at the end. And the calibrated measurements look like this, that we don't take the argument of the phase of the measured reflection coefficient compensated by the offset, but there is an additional point which we add here, the self-RCS calibration constant, to perform calibrated measurements. Again, if you're interested in the math, please visit the papers from the previous slide. And in the next slide, I will show you the effects of this calibration. If you repeat all those measurements and apply this calibration, this is what you get. Here we again see the accuracy or the error curves showing what happens if the self-RCS become neglected. So these are the lighter curves, and the darker curves refer to the application of the self-RCS compensation. And what we can see that consistently the self-RCS improves the accuracy we get. So we obtain very low errors compared to when we would neglect the RCS. And the same applies also to the monitoring of vibrations. This is the spectra you would obtain. And just to make the point a little bit more clearer, if you only see the self-RCS compensated results, this is how the spectra look like. So only basically we have only the intended oscillation detected by this radar sensor, and all of the harmonics are gone. So the self-RCS compensation linearizes the transfer function. At this point, we only applied the perfect calibrated vector network analyzer, so we don't have any imperfections of the hardware. And if you want to use this calibration technique to practical radar transceivers, it's also applicable. So the method can be adapted or extended to practical transceivers. This is something which we also shown in a conference contribution here when you're invited to see the details there. But it works. So in a practical transceiver, you get an ellipse instead of a circle, but the method proposed there compensates for the IQ imperfections, the in-phase and quadrature imperfections, as well as the self-RCS all in one piece. Well, to summarize, we have conducted all these measurements also for different reference distance. So in the previous slides, we have the 1 meter reference distance. And in this, we can see from this plot that consistently the results with the self-RCS compensation, they significantly reduce the error up to several micrometers only. And if we disregard the compensation, the error increases with the housing size. And this holds more or less true for the other reference distance. So the self-RCS compensation consistently reduces the peak-to-peak error. And without the compensation, the errors may fluctuate. And at this point, you might ask yourself, why are those errors changing with distance? Because we had actually a constant self-radar cross-section. And this point, I hope, would become more clearer if we go to the next section, which will deal with the near-field effects. But all in all, the neglection of self-RCS leads to reduced accuracy, and it introduces a nonlinear behavior of the measurement transfer function, and the self-RCS compensation can compensate for this effectively independent of the particular self-RCS of our system. Well, let's move to the next topic, which, as I said in the beginning, from my personal perspective, is the most exciting or interesting one. And this is the topic of near-field effects. To motivate what do we mean by near-field effects, we again start with a very basic example. On the left-hand side, we have now again a target, a disk, which is now 150 millimeter in diameter. And if you look up some theory, you would can calculate that this target has an RCS of 14 dBSM. On the right-hand side, we again have an antenna, and this time a horn antenna. And it's again calibrated with respect to this reference plane, and we again measure the input reflection coefficient. We are operating at 24 gigahertz with a wavelength of 12.5 millimeter. In this basic setup, everything is perfect, and in order to describe the receive power, we can, of course, or we can try to apply the radar equation. We have the gain of the antenna, we have the wavelength, we have the range, and we have the radar cross-section. And if we put everything into this formula, this is the result you'll obtain. And here we plot the relative receive power on the vertical axis and the distance on the horizontal axis. This is the theory, but if you perform the measurement, this is actually what you observe. First of all, there's some offset, but now we have some minimum and a maximum and again a minimum. And this is somehow contradictory to our perfect response observed according to the radar equation. And also you might wonder what happens actually at this point. So at this point, the radar equation would suggest a receive power which is higher than, the relative receive power is higher than 0 dB or larger than 1. So actually you would receive more power than we transmitted. It's something unphysical, right? And the idea why it's the case is actually that we are violating some fundamental assumptions related to the radar equation. And the blue curve is actually the ground truth measured, right? So we now want to explain why does this curve look like this. For this, we consider again this fundamental relationship between the antenna and the target. And if the wave which is propagating to the target, it's reflected, the key property to describes this is, of course, the radar cross-section. The radar cross-section is an inherent property of the target. So we can completely analyze or describe the radar cross-section of a target independent of the antenna or the radar technology. It's an inherent property of the target. And for this, one assumes far-field properties. And for this, one assumes also that there's a plane wave impinging on a target across the entire surface of the target. And we evaluate the relative power or power density related to a plane wave observed at infinite distance from the target. When dealing with far field or near field, in terms of antenna or associated with antennas, it's also always the question to ask whether the target is in the far field of the antenna. And to answer this question, one usually applies the rule of thumb, which is the 2 times the aperture size squared divided by the wavelength. But the same question can also be put from the perspective of the target. So the target also might ask itself, is actually the antenna in the far field of the target? And this is not always the case. So here we see an example where the antenna is actually in the near field of the target. So also the target cell, it has an electromagnetic extension. And here we can also apply the 2d squared over lambda formula to approximate where the far field distance is for the scattering field. So we want to find out where we can assume that the field scattered by the target is or behaves like a plane wave, because this is critical to apply the radar cross-section and the radar equation concept. For the example we have illustrated in the beginning of the section, when we put those numbers in of a target of 150 millimeter in size and a wavelength of 12.5 millimeter, the far field range is actually 3.6 millimeters. 3.6 meters, sorry, and we were measuring below 3.6 meters. And this is actually the point which is important here. The radar cross-section in such a scenario, because it is a far-field quantity, it is not meaningful here to describe the system behavior. And the reason for this is visualized in this slide. So the antenna also is not a plane wave generator in short-range configurations. It has a radiation characteristic, of course, and here it's described by the gain pattern G of theta and phi. And when we want to estimate what is actually the field that is impinging on the target, or it is illuminating the target, there will be a spatial selectivity or a weighting of the antenna introduced to the field which approaches the target. This is not a plane wave. And similarly, the scattering contributions may all look a little bit different depending from what kind of directions they are coming, because of the inhomogeneous illumination, and also from the receiving point of view, the antenna weights different reflection portions differently because it has spatial selectivity. And this makes the point that in the short-range applications, we cannot use the radar cross-section, but we need to study the entire radar channel transfer function, which encompasses the antenna and the target. So we need to study them as a combined system. In the next slides, I will briefly go through how to derive a radar channel transfer functions, which allows for a simple analytical overview about what's happening in the short-range applications. So the beginning of this are the Stratton-Chu equations, which lead to which are a basic formula which can be applied to estimate the scattered magnetic field at some point. Right? This is our starting point, and from this on, we make some assumptions. We make the assumption that the target is electrically large, that the radii of curvature are significantly larger than the wavelength, and for the purpose of simplification, we assume that this is a perfect electrical conductor. Based on these approximations, one arrives at the so-called physical optics approximation, which is often used when studying targets which are electrically large. This is what we also assume here. Now, from this point of view, we would need to estimate the incident field, and for this, we make an assumption. We assume that the target actually is in the far field of the antenna, but the reverse is not true. So the antenna can be located in the near field of the target. So since the target is in the far field of the antenna, we can use the spherical wave propagation and the far field gain and phase pattern of the antenna to estimate the incident field on the target surface. Then there is another point. So the question is actually, do we need to evaluate the scattered fields? And the answer to this is actually not for a radar application. When you're looking only for propagation of radar of electromagnetic signals, you would like to have the scattered field, but for the radar, it's important what's actually induced in the terminal of the antenna and not what is the field outside of the antenna. And for this, instead of integrating here just to evaluate the field, we consider that all of the contributions of the field are individually received by the antenna and weighted according to the gain and phase pattern associated with the respective observation direction of the antenna. If you do all of the math, you will arrive at this monostatic radar channel transfer function, which looks very compact, and it can be categorized or grouped in 3 different terms. The first one is associated with a target shape, then with a term associated with the free space propagation, and finally, we have the term associated with the antenna. And all of these contributions are summarized or integrated over the target surface. So the target surface, as we can evaluate this integrand, this function, for each element of the target surface, and the response is the integral of this. If you're interested in the details of the derivations, I refer here to the respective papers, so feel free to look ahead and dive into the details. But in summary, we combine here physical optics principles with the antenna radiation pattern. We assume that the target is in the antenna far field, whereas the antenna can be located in the target near field. This is the critical point. And the target is electrically large without edges or re-entrant structures. It is not meant to be a full wave solution. It is an approximation just to get an intuition for what's happening in the short range applications. Well, let's validate the derived transfer function. And here again, so some measurement setup. Ideal conditions, we have 2 antennas with different directivities, a horn antenna and an open-ended waveguide antenna with directivities of 9 dBi and 80 dBi. and targets of different sizes from 50 millimeter up to 250 millimeter. On the bottom here, you can see the normalized linear directivities plotted on top of each other. So the horn, of course, has a higher spatial selectivity than the low directivity open-ended waveguide. And these are the responses you observe. So this is what we had in the very example from the very beginning of this section. And what we also see is when we get higher in diameter of the target, the larger target, we receive different characteristic with more minima and maxima, whereas for the small target, we actually get a response which is quite familiar with the radar equation. And these effects which can be termed as power fading effects, devoted to or associated with the near field conditions here. What we see, of course, is the measurement and the proposed simulation. They are quite very well matched. So the model we have developed can be well applied to study the behavior of the radar channel in the short range configuration. The other benefit is that we do not only use the magnitude as by the radar equation, we also look at the phase, because the phase is also critical when working with radar signals, right? It is related to the time delay. And in the phase, we also observe a distortion because of the near field effects. What we see plotted here is basically the difference between the perfect linear response in far field to what is measured or simulated in the near field condition. Right? So ideally, would observe a line which is at zero constantly. Right? So we are referring to the difference of the perfect linear far field response. And if you look at this difference in the near field conditions, we observe some very nice looking distortions, which are scaling with the target size, and also depending on the directivity use, we have also slightly different responses. And by the way, you may wonder why all this curves a little bit thicker. Here's a zoom in window, and here you have the greetings of the self-RCS effect, which is not compensated here. Okay, the question is, why do the minima and maxima arise at all? So the radar channel transfer function, as we derived, is basically a complex valued function, epsilon, which is integrated over the target surface. And for the example of the 150 millimeter disk, these were the results. And by this example, I would try to explain why the radar channel transfer function experiences those minima and maxima. For this, we'll plot this complex valued transfer function on the target surface. And we do this with this two-dimensional color map. So in this axis, the colors represent the phase of this function. And the opacity of the color bar indicates the normalized magnitude of this complex values function. This will become more clear if we look at the examples. So here is a target disk, and on this target disk, we display this function in the far field condition. And what we observe, we have a perfect flat phase response across the entire disk. Since we are in the far field, the entire phase contribution is equal, and we have a homogeneous elimination. But when we move closer to the target, for instance, this point, at this point, or this point, we are receiving a phase gradient of this function. And this is the key point which leads to the near field effects. When we look at those two candidates here as an example, we can very well explain why this one leads to a minimum and why this one is leading to a maximum. So when we observe the phase measured in the center, it is normalized to 0 degree. And once we move outside, the phase changes from to about pi. And in this example, there is a gradual phase shift, and we are observing phases which are from 0 to minus pi over plus pi again to 0. And this will lead to destructive and, in this example, constructive interference. So these two candidates we are taking on the next slide. And in this slide, we will perform actually the integration. On the right-hand side, we will show the result of this evaluation of the integral. and we'll integrate from the 0 point, or the center of the circle of the disk, and we'll move outwards, and we'll integrate all of the contributions across the azimuthal coordinate. And this is what one observes. When we're integrating over the target disk, we are adding up complex phasors basically for each subsurface element of the target disk. And finally, we arrive at the result. And the result is that for this disk, because of those counterphase cancellations, we observe a very low receive power, whereas in this part, we do not have this destructive interference, and we observe a higher receive power level. There is also a dependence on the antenna directivity, and this slide basically, and the next one should show this. So these are the responses for the open-ended waveguide. And if you look close now, very specific one to this discs, you will observe a difference when you move on to the horn, right? So you see there's a difference in the opacity, and the opacity basically scales the magnitude of those functions. And this also makes sense because of the higher selectivity of the horn antenna. The outer portions of the target are fade out, and they're contributing less to the overall response of the radar channel transfer function. Now, do those effects also apply to real-world target shapes, for instance, in the perspective of medical radar? And the answer is, of course, yes, and they become even more severe. And this is what we want to look next. So in order to simulate this for real-world target shapes, you cannot describe, for instance, such as torso in an analytical manner, but you can use some 3D model descriptions. So we had a simulation framework presented at the last year European Microwave Conference. Here you can see the details where you can use an STL file target model, a simulated antenna far-field radiation pattern, and apply the radar channel transfer function derived in a numerical discretization approximation to arrive at the radar channel transfer function. Regarding the validation here, we consider this setup where we have a mannequin which mimics a human body. It is fully metallized to comply with the assumptions we made, and we use two different types of frequencies and 3D printed antennas, which are designed to have the same directivity of 18 dBi. And we selected some arbitrary 4 positions here, and at each of the position, we will shift the antenna from 0.2 meter to 0.5 meter and measure the radar channel transfer function. And of course, this is a short-range configuration and near-field configuration. If you would evaluate the rule of thumb far-field distance for this size, you will definitely be over 10-meter distance where you could assume far-field conditions. And here we are very, very in the near-field conditions. These are the results. Again, proposed simulation and measurement, they agree quite nicely with each other. But what we observe, you have different characteristics depending on the position where you are measuring, right? So the curves you are obtaining there look different. They differ in frequency. Also, you have different responses. For instance, here you have a sharp minimum at 61 gigahertz, where it's and here you have a maximum, whereas at 24 gigahertz you have a maximum here, and in the other position there is quite a different response. Similar applies also for the phase response. Again, we show here the deviation of the ideal far-field linear response when we would move the antenna away from the target. And here also we do not get the perfect zero line, as would be the case in the far-field conditions. We have a distortion of the phase, which is not only linear, so it's not indicating a virtual increase or decrease in the effective wave number. It also is distorted in a nonlinear fashion. And the reason for this is, again, lies in the integrand of this radar channel transfer function, which is animated here. So again, we plot the integrand epsilon of S on the surface of the target with this 2D color map. And once the antenna approaches the target, the target actually from electromagnetic perspective looks different because the radar channel transfer function we evaluate is basically the summation of all of the points here, which exhibits a color. And if we have close proximity between the antenna and the target, we have, from the perspective of electromagnetics, we have a different target, different contributions to the radar channel, which justifies why we observe different responses depending on the position as well as the distance. Well, the near field effects, they're quite severe when we look for targets which are very large electromagnetically. And this has the consequence that we also will observe a very high variability when we change the antenna position. And this is the next topic of the presentation, the radar channel variability. In this, we would like to investigate, at the example of the medical radar application, what actually happens if we move the antenna in the transversal plane relative to our target. So the delta x and the delta y is the change of the antenna position, and we want to evaluate how strongly is the receive signal affected by those small shifts. From an application point of view, if you look at medical radar, when the person, for instance, is sitting in front of the radar, such small random variations of the relative positions, they're inevitable. So you cannot convince and a person that sits perfectly still. It's not possible. So there are always some random, small scale movements between the target and the antenna. This is we investigated again by measurements and compared this to the derived radar channel transfer function. We have a very similar setup as before, but now we use, let's say, a reference measurement with a 24 gigahertz horn antenna. Then we have a 24 gigahertz open-ended waveguide antenna. And to study the effect of change of frequency, we have the same antenna characteristic, but a frequency of 61 gigahertz. And of course, 24 gigahertz and 61 gigahertz, they're referring to the ISM band frequencies where typically one would want to locate such medical radar applications. And now we are performing a scan in the plane transversal to the mannequin, and this is indicated here. So the plane selected is a rectangular plane of 300 millimeter times 400 millimeter, and in this plane we'll position the antenna at some equidistant grid, and we are measuring about half a meter away from the target. These are the results, and just to make sure these results do not show any fields or field distributions, what we see here is that at each point in this coordinate grid, the color basically marks the value of the magnitude of the radar channel transfer function on the left-hand side and the phase on the right-hand side. What we observe here are very strong fluctuations of the receive power when we look at the open and the waveguide antenna at 24 gigahertz. In addition to this, also the phase varies very strongly. So if we just move a little bit from a reference point, the phase fluctuates a lot. The good thing is we can very much predict this by simulation. So the simulation result and the measurement results, they match quite well with each other. Now the question is, what happens if you would change the antenna characteristic? Under far-field conditions, you would assume there's only a receive power level increase, right? Because we have a higher gain antenna. But in the near field, this is not the only thing which happens. And what we observe, and again, look at the difference, this is the open-ended waveguide antenna, this is the horn antenna, also the characteristic of the response changes. And this is because the antenna directivity leads to a different selection of the integrand contributions, which make up the total radar channel transfer function. And again, that proposed simulation will predict what is being measured in a physical environment. The reason for this, again, looking at the radar channel transfer function derivation, we had there the term which is only affecting the properties of the antenna. Everything here is constant between those two measurements. Only the antenna is changing. And if you again evaluate this integrand, so basically this function inside the integral, for those two cases, you see that you have different kind of targets. And this is the key to understand why the actual responses for the spatial variability are looking different. Moving again back to the reference measurement with the 24 gigahertz horn antenna, you can see directly the difference, what happens if you go to the 61 gigahertz and do not change the directivity, right? Again, just to make the point clear, this is the change of frequency. And well, this would be quite familiar from far-field responses also, because there is also a difference between the frequency, of course, this is something natural, but in the near-field conditions, we are basically even more in the near field at the higher frequency. And again, looking at the integrands, we see the only thing which changes is the free space propagation term. The frequency is actually hidden here in the wave number, right? So the wave number is 2 pi over the wavelength. So this is where the frequency comes in. All the other parts are constant, and the integrands, again, plotted on the target surface, they look different. To sum up all of these results for the level of 500 millimeters, I've provided you a small gallery of those simulation and measurement results to see all of them at one glance. And now we want to answer the question, what's happening when you reduce the distance? And if you reduce the distance, this is how the characteristics look like. So in the slide before, we have a distance of about a half a meter, and now we have a 20 centimeter distance. And these results look quite different of the spatial characteristic than those at 500 millimeter, which justifies why it's important in short-range configuration to deal with these topics, because this is not a perfect radar equation-like scenario. The distance change, the transversal change in positioning may strongly affect what is actually being received. And in terms of an application where there is a strong fluctuation between those relative positions, this might be critical for the success of those applications. Well, since those radar channel transfer functions, they're varying a lot, to get, let's say, some rule of thumbs or an assessment of how strong these variations are, it is beneficial to evaluate them in a statistical manner. And this is what we are doing in the next slide. And here we select some area of the measurement area where we would assume in this area we would like to position our radar sensor to measure medical, to perform the medical radar application. So if you subselect this region and evaluate the statistical distribution of the receive power level, this is what we observe as a cumulative distribution of the receive power. And what we see here, we do not only get one receive power, of course, we have a certain variation of receive power. And the variation of receive power can be quite severe. So it can even reach 30 dB of receive power statistical spread in this small area, right, which is only about 20 centimeters at the same distance from the target. And of course, we have the difference between the directivities. This is also something which is not the case in the radar equation-like world, but is a key aspect in the near field or short range configuration. And the last point I would like to focus on is not only the spread of the receive power levels, but also the local variability of the radar channel. Again, when we look at this sub-selected area where we would like to position our antenna over the target or the chest of the human body to measure medical or vital signs, we say, for instance, this is the antenna position, and around this position we define a local window of a size S by S. And for this local window, we evaluate two parameters. And the first one is the magnitude variability. I admit the formula looks quite strange or big, but this is basically a very simple what's it's telling. We take all of the magnitudes inside this local window and consider the maximum value and the minimum value and consider the difference in dB. So we are looking basically at the local dynamic range within this local window. Now we will evaluate how strongly the amplitude is changing within this small window, and we perform this measure for all antenna positions. The similar thing is also conducted for the phase variability. So here we again look what is the phase at our antenna position, and within this local window, what is the maximum change in phase, and we evaluate this for all positions. The responses we get in a statistical manner are shown in this slide, and it's very important to note that the local window we are selecting is just 1 millimeter, right? It is thinner than a coin. And for this small local window, we can observe that there are a lot of magnitude variations and phase variations. So for instance, in this magnitude variability plot, we can observe that horn at 24 gigahertz, half of the positions would lead to a variation of 1 dB, whereas for a 61 gigahertz horn, the variations would be at 2 dB. And for the phase variability, which is also important, right? Because from the phase, we want to extract the medical parameters or the mechanical motion. We observe that even small variations of 1 millimeter in the transversal plane may lead to very strong fluctuations. So half of the antenna positions lead to a phase variation less than 10 millimeter, but there's another half of the positions where the phase variability is higher than 10 millimeter. And also the antenna directivity plays a crucial role. So it's going from the open-end waveguide to the horn antenna, the characteristics are changing, and this is something which one would not expect from classical radar equation point of view. Well, this brings me to the conclusion of this presentation. And in this conclusion, I would like to provide the overview of the relevant effects in short-range radar applications we focused in this presentation. The first part is the self-RCS, so the self-radar cross-section. Radar sensors or antennas of radar sensors that are not invisible or for radar, they have their own radar cross-section, and this leads to multiple reflections between the target and the antenna, which then reduces the measurement accuracy. There are nonlinear distortions, but we can compensate for them with a dedicated compensation procedure. Then the second part were the near-field effects. And for the near-field effects, it is critical to note that the antenna is in the near field of an electrically large target. It is not in the far field. We don't need only to consider the antenna or the far field, near field conditions from the perspective of the antenna. Also, we need to discuss this topic from the perspective of the target, where we want to answer when or at which distance we can assume that the scattered field is a plane wave. For the near field effects, we have to mention the received power fading and also the nonlinear phase distortion, and we provided a tailored simulation model to account for these effects with some assumptions made. Last but not least are the radar channel variability effects, and here we have seen that even small spatial variations induce large signal variations, which may fluctuations, which may be very critical from the application viewpoint. The effects are antenna dependent, right? So the directivity of the antenna matters a lot here, and we provided a statistical evaluation to get a better overview of the statistical distribution of these effects. With this, I would like to thank you very much for attending this presentation, and I will be very happy if you have some questions in this webinar, or if you have some questions later on, feel free to contact me. On the left-hand side, you can see the address or the contact information. So thank you very much, and I'm open for questions.
Yeah, thank you, Bartosz, as well for this very, very interesting talk. So there was quite a lot of topics, quite broad, but really impressive work. There are already a few questions. I'm not sure if you also already opened the window, Bartosz, so I will read them to you, and maybe we can discuss them afterwards. So the first question, did you use 3D models of the human body in the near-field radar sensing simulation?
Okay, very good question. So we actually had this mannequin, right? And we taken a 3D scanner to obtain a 3D model of this human body. And this model was then used to the simulations, right? So the accuracy or the scanning accuracy was sufficient to operate or to provide a sufficiently accurate model for the 61 gigahertz cases. And yes, so the answer to this question, we had the exact digital twin, so to say, from mechanical viewpoint of the target we measured.
Hmm. So next question would be, what do you think about the idea that in the near field sensing, the energy from the distributed antenna beam is focused point by point on the object? So I guess it relates a bit into the direction of if a focused antenna would improve your setup.
So this is a point we are definitely working on. So in the short range configuration or the near field configuration, the only thing you can actually do is, let's say, change frequency, change position, or change the antenna characteristics, right? Because it is the interface which determines which portions of the target actually are contributing to the receive signal. And here, this is definitely something where the solution of the near field effects lies in, and this is something which we are also currently working on. And maybe in the next European Microwave Conference, you also will see some contribution in this regard. But usually applying focusing is related to increasing the antenna size, right? So if you want to have a higher directivity or even a near field focus, you need to increase the antenna size. And this is then leads to the fact that also the target is located in the near field of the antenna, and also the antenna size is becoming larger. So also those self-RCS effects can become even more crucial and also depend on distance, yeah, because also then the self-RCS of the system or the antenna or your radar sensor is becoming a near field effective self-RCS. So it may be a solution, but it can be also that there are further challenges which are overseen at the moment.
Okay, thank you. So the next question is, which differences can you identify for the three effects if you adopt a modulated radar waveform with high resolution?
Mhm. Yeah, very interesting questions. I see all of them trigger actually my current research. So as I said, looking at the continuous wave perspective is serves as a basis, right? Because we are looking from a, let's say, from system point of view on the frequency response. If you have modulated waveforms, you want to look at the time domain response. But from the frequency domain response, you can easily go to the time domain response and deduce the effects there. And as long as you have some, let's say, frequency selective response in the frequency domain, you will also obtain some effects in the time domain response. And even if you would apply very high resolution radar or a very large bandwidth, you might expect, again, let's say from far field perspectives, everything would be better because you could somehow discriminate individual contributions which can be discriminated in range. But I can promise you also in the near field, there will be some effects which you maybe see also in the future, which cannot be just neglected. And the near field conditions, they are very, very interesting. So it's quite interesting to apply all of the knowledge from the far field relationships, and some of them also somehow apply to this, but there is always some additional aspect one needs to consider.
Maybe I just ask a question myself because I touches upon at my own field, right? So as you know, Bartosz, I'm doing a lot in really wideband radar signal processing, and maybe I just missed it in the beginning. So just for just to get an idea of it, what was it? So you considered all these topics purely CW, or do you consider a certain bandwidth within your system?
In all of the topics in the presentation, we considered purely continuous wave operation,
Uh-huh.
single carrier,
Uh-huh.
no modulation, no
Okay.
response. So we are basically using like a reflectometer, right? We
Uh-huh.
measure phase differences. But
Mhm.
like I said, the transition from a continuous wave operation or the effects which arise there to
Mhm.
modulated waveforms. Let's say the theoretical fundamentals to do so is established by this, right? Because if you have a transfer function in a frequency domain, you can apply, for instance, the evaluations here to see what is actually the time domain or the impulse response of this. And by this, you can also see what is happening from the frequency domain viewpoint. If you look,
Mm.
for instance, from a frequency modulated continuous wave radar, so on the FMCW radar, the point is basically quite clear. If you see the differences between the 24 gigahertz and the 61 gigahertz measurements, there is for sure a transition in the response, and you are getting a frequency selective response of a frequency. And this is
Mm.
something which will then change the response you're observing from a perfect ultra wideband system, which are
Mm.
effects which are similar to, let's say, a frequency response of an amplifier or a mixer or something like this. But these are related to the radar channel, right? Those
Mm.
effects in the transceiver, you can try to compensate for this. Of course, for a wideband operation, it's not a very easy task, but here the multidimensionality is even more increased because you have a dynamically changing radar channel, and
Mm.
all of these superimposes to the frequency selectivity.
Mm. Maybe just as a short follow-up. So one could, in principle, I guess, scale your simulation or yeah, iterate your simulations over different frequencies to capture the wideband behavior, right?
Of
And as
course.
you've shown, the computational load, let's say, seems to be yeah, seems to allow this because you at least did the spatial scanning,
Yeah.
right? So just to get an idea, how long does a single simulation with your
So I
mannequin
can I
take?
can I can say time is actually no problem
Okay.
because the evaluation here is there's no solution of any equations. This is just evaluation of a function or a summation.
Mm.
And this contribution from the previous European Microwave Conference, this is actually was the focus of this, like to have a fast evaluation of this. And we implemented those spatial scans on a, GPU, of course, to speed it up even further, because all of the evaluations are parallelizable, so they can be executed in parallel. And for all of the two-dimensional scans, depending, of course, of your architecture you're using, but you definitely are below 1 minute for all of
Okay.
these
Okay.
large scans. And
Yeah.
if you only look at this one dimensional scans, where you had, if I remember correctly, 4 times or in total 6,000 positions, the evaluation time was 3 seconds.
Mm. Okay. So
But for the ultra wideband system, you would
yeah.
also need to discretize the frequency axis, of
Mm.
course. And this is a point.
Yeah.
And you would also, for sure, take to account the frequency response of your antenna, because
Yeah.
also the directivity is changing
Bartosz,
with the.
sorry, I don't want to interrupt you, but I see there are many, many questions. I
Okay,
think I got the point, and maybe both of us do a follow-up discussion afterwards
I'm
or in the
fine with
next
this.
days. And then I'll prefer to answer the questions from the audience for now. Thank you very much.
Okay.
Okay. Where have we been? Okay, so there's a question from University of Bern. So Bartosz, thanks for the interesting presentation. I was wondering if the simulation model for the Phantom is also based on physical optics and a PEG target, the model you used in the self RCS, or the modeling was different. Guess it was the same, right?
Um, I was so I'm reading the question also.
Yeah.
So the model we so for the comparison between the phantom measurements and the simulation, we used the 3D scanned model of this physical 3D mannequin. And this model applied the physical optics principles or the derivation. I show you the radial transfer function, where we have the integration of the over the surface of this body. For the self RCS effects in the first part of the presentation, we there assumed far field conditions, yeah, to admit it, just to make this or separate those two things. But of course, in the practical measurement, you have also in the near field the effects of the self-RCS, but they were not included in the physical optics simulation, right? These effects were neglected there. If you want, you can account for them in the simulation, but this would enlarge the computational load. And to be honest, from the basically variability point of view, it would not change very much the results. You would have local oscillatory fluctuations, but if you would look on these pictures, yeah, because the measurement they included the self-RCS, of course. Yeah, you cannot turn this off in physics. The responses are very, very similar. Because the self-RCS effect is an effect which is very critical if you go for accuracy.
Hmm.
I hope this answered the question.
Yeah, sure. So the next question would be, do you consider an advantage to illuminate the target with a plane wave?
Oh, this is a very good question. I would like to do so, but in the short range configuration, this is not possible. If you have a practical radar scenario, you put your antenna in front, for instance, the human body or the other target, a machine or so. The machine or the target is at 1 meter distance, and you cannot change this. And if you evaluate the phase or the magnitude of the antenna around the antenna at the distance of 1 meter, of course, the antenna spreads spherically from its location. And only if you're very, very far away and you consider a small solid angle or a small viewpoint, you can approximate the field by a plane wave. But by nature, the field distribution or the propagation is a spherical nature. And at the short distances for the short range configurations, there's no possibility to assume a plane wave. Because the result, you can obtain a result in simulation, but they will not apply if you want to deduce the response of your radar system for this configuration.
Hmm. Um, Next one would be, thank you for the excellent talk. Does antenna bandwidth have any impact on phase stability or multipass effects that could influence your self-RCS calibration?
Mhm. So the multipath effects, of course, in the model I have shown you, they are not included there, right? So the model assumes that there is only interaction or a direct interaction between the target and the antenna or the radar sensor. There are no effects from multipath propagation. They're excluded there. And of course, in a practical environment, they also contribute to this. But if you consider that only the target performs dynamic motion, so if it's moving over time, and the multiple path propagation, they are somehow correlated with this, right? And from a continuous wave perspective and using one antenna without yeah, angular resolution, you cannot discriminate those either. So of course, these effects, they influence the self-RCS calibration. And if you have multiple of problems, which is basically, I would say, a fourth big issue when you have short range configuration, that you also have multipath effects. Those self-RCS calibration presented has its weaknesses, of course.
Um, Maybe I skip to the next question first because I think it touches the same topic, which would be, is it possible to apply the calibration for self-RCS in MIMO radars where the angle estimation of the target is also required?
Very, very interesting. So since we are also dealing a little bit on multiple input, multiple output radars, this is also a question we put ourselves. And the answer is yes and no. Let's say from a theoretical perspective, it's feasible. The only thing you need to acquire here is that you have a angle-dependent radar cross-section of your antenna or your radar sensor, like any target. There's not an isotropic scattering pattern, but it is an selective, a spatially selective pattern. And from a practical viewpoint, you would need to store all of these self RCS calibration coefficients depending on angle. And here the problem becomes you first need to estimate from which angle the wave is arriving to select the correct calibration constants. So maybe one can resolve this or have some estimate and then iteratively find the correct angle with the self-RCS calibration included. But from theory viewpoint, you could also apply the self-RCS calibration for multiple input, multiple output radars.
Hmm. Yeah, I'm wondering in this regard, your calibration method was derived basically from a one port VNA situation, like a three-term error calibration.
Mhm.
In case of the MIMO system, you have something like a two-port configuration, right? So
It depends how you generalize this, because
yeah.
let's say in the digital domain at the end, or if you would do this analog in the analog domain, you would also sum these two ports up with some phase shift
Mhm.
and amplitude if you want. So
Mhm.
I believe you can generalize this to multi-ports also. And if you want to extend this, you can also introduce the coupling effects between those channels in order to make it more closer to the physics. But I believe it's still adaptable to this
Okay.
because effectively you can also apply some. If you consider you would have two of the signal flow graphs next to each other, at the end you would have again a summation block of these responses with some phase shift. This would extend your model.
Mhm. Okay. Yeah, so I guess it's also related to the very last question. So then we skip back to the one that we skipped before. What about signal reflection from tissues inside the human body?
Mhm. So since we are dealing at, let's say, millimeter wave frequencies, so if you include 24 gigahertz also in the millimeter wave range, you can evaluate basically the penetration depth into the tissue. And if you do this, there's also, we have um, included this in one of our publications. This is everything which is basically interacting behind the skin. This is completely neglectable. So each of every power contribution there is simply neglectable or negligible. And of course, if you would go to lower frequencies, this is something you would need to consider, of course. But at the millimeter wave frequencies, the the practical response from the human body is associated with the surface, and the absorption losses can be just accounted for. But there are no, let's say, interactions from the inside of the tissue.
Okay. So I guess we're done. So thank you very much, Bartosz, for this very interesting session with you.
I also
So
thank you very much for the invitation.
yeah, and yeah, thank you to the audience as well for uh, giving us such a fruitful discussion here, and yeah, the quite nice number of attendees. Yeah, as always, we will upload the webinar in a few days on YouTube, so you're invited to share it, and yeah, hopefully join our next installment of the series, which will be in already at the end of June, I think. So stay tuned and have a nice afternoon. Bye bye.
Bye.